Hi everyone, I'm Zhuo from Tsinghua University. I'm going to talk about our paper, Transparent Classification with Multilayer Logical Perception and Random Binarization. This is a joint work with Zhang Linliu and Professor Jian Wang. Relying on the strong ability of data modeling, machine learning, especially deep learning, has a widespread usage in many important areas such as medicine, finance, politics, as well as law. In these important areas, people need explanation for why decisions are made to ensure their safety and protect their rights. As a result, the demand for the transparency of machine learning method is increasing. Here, the notion of transparency is that each part of the model, including input, parameters, and calculation, admit an intuitive explanation. However, most widely used machine learning models, including deep neural networks and ensemble models, are considered as blank box. Therefore, we can hardly understand and explain them. There are many works trying to obtain a transparent or interpretable model with good prediction performance. Rule-based models, including decision trees, rule sets, and rule lists, use logical rules to build the model. Their inner structures are transparent, but they suffer from lacking an efficient optimization algorithm because of the discrete parameters. Surrogate models use a transparent model to fit the complex model locally or globally, then explain the complex model by interpreting the transparent model. However, inconsistencies always exist between an actual model and its surrogate model. Hidden layer investigations visualize and analyze status of hidden neurons or their learned features. They are intuitive with visualization, but it could hardly be quantitatively measured and applied. Binary neural networks train a deep neural network with binary weights. However, only binary weights are not enough. Binary neural networks are still much more complex than rule-based models. We aim to obtain a model with both transparency in the structure and high classification performance. However, most of the related works try to interpret those learned complex models, which are hard to understand and the interpretations may be inconsistent. Why don't we try the opposite way to solve the problem, that is, improving the performance of transparent models? As mentioned before, rule-based models have both transparent inner structure and strong model expressivity, but suffer from lacking an efficient optimization method because of the discrete parameters. If we can reduce the gap between actual performance and the optimal performance of rule-based models, we may obtain a model with both transparency and high performance. But how can we reduce the gap? To answer this question, we first propose a new model structure named Concept Rule Sets, abbreviated as CRS. Before giving the definition of CRS, let's first formulate the concept of rule and rule set. A rule is a conjunction of one or more Boolean variables, while a rule set is a disjunction of one or more rules. One CRS is a multi-level structure in which each level contains a conjunction layer followed by a disjunction layer. A two-level CRS is shown in the figure. The left side and the right side are two forms of CRS. The bottom layer is the input layer, and nodes in the input layer represent features after the discretization and binarization. The next layer is a conjunction layer, then a disjunction layer. Nodes in conjunction layers correspond to one rule, while nodes in disjunction layers correspond to one rule set. If there is an edge from node A to node B, it indicates that A is one of the elements in the logical operation represented by B. For example, in the figure, R1 and R3 are connected to S1. It represents the equation S1 equal R1 or R3. The matrix W superscript L denotes the adjacency matrix of the L's layer and the L-1's layer. We can see that one level in CIS is equal to the widely used model. rule sets, and the multi-level structure of CIS increases the model capability further. If we set the number of nodes in the last layer to the number of class labels, CIS can work as a classifier. Meanwhile, a crucial byproduct of CIS is a learned layer-wise representation of each instance, similar to the mechanism of deep neural networks, but more transparent. Let H superscript L denote the data representation learned by the else layer in CIS, which is a binary vector, and each dimension corresponds to a rule or a rule set. We can understand each dimension of this binary vector by analyzing the corresponding rule or rule set. It is much easier than analyzing the real valued weights and the activation value of hidden neuron in deep neural networks. For CIS, it's very similar to multilayer perceptron. One idea is trying to train CIS like MLP. We propose a new neural network called Multilayer Logical Perceptron and a tailored training method, which can search the discrete solution of CIS in a continuous space using gradient descent. There are two main differences between CIS and MLP. The weights of MLP are real-valued rather than binary. In MLP, we use activation functions instead of logical operations. To train CIS using MLP, first we need to find an activation function that could simulate the conjunction and disjunction operation. We adopt the conjunction function and disjunction function proposed by Peony and Fackery. These two functions use multiplication to simulate the logical operation, and if the input and the weights are all binary, they are equal to the corresponding logical operations. We can see that function fc and fd work as selectors, and they only select hj to participate the operation when wij equals 1. In other words, they replace hj with the value that cannot affect the final result when wij equals 0. To maintain the characteristic of conjunction and disjunction functions, we concentrate all the weights of MLP in the range from 0 to 1. Here is the loss function. It is very simple. The MSE criterion aims to minimize the gap between the continuous output vector and one hot label vector in each dimension, which could benefit the discrete CIS extraction. The L2 regularization encourages the MLP to search for a CIS model with shorter rules. Two reasons could cause the vanishing gradient problem. One is the constraint function. If we use the sigmoid function to restrict the weights, the derivative is close to 0 when sigmoid wij is close to 0 or 1. However, we aim to learn the weights close to 0 or 1, which means derivatives close to 0 are inevitable. We use Schlip function to deal with this problem. Schlip function is similar to the ReLU function, but it concentrates the output no more than 1. We only need to use Schlip function to constrain the weights after updating them with gradients. The other reason for the vanishing gradient problem can be found by analyzing the partial derivative of each neuron with respect to its directly connected weights. We can see that in the heat map that only when W is close to 0, the Fc times 1 minus Fd is close to 1. If most of the weights are not close to 1, either Fc or 1 minus Fd is less than 1, then the product of a sequence of Fc or 1 minus Fd could be very close to 0, which also means the gradients could be very close to 0. Therefore, A simple but efficient solution is to initialize the weights with small value close to 0. After training the MLLP, we need to extract the discrete CIS from it. A straightforward approach is to binarize all the weights using a threshold. However, the behavior of extracted CIS is very different from MLP, and the extracted CIS can hardly be used for classification, especially when MLP is deep. One example is shown in the table. We can see that the logical activation function does not play the role of conjunction operators as we expected due to the real-valued weights, and this problem is caused during the training process. To tackle this problem, we propose a new training method called random binarization, abbreviated as RB. One example of RB method is shown in the figure. When using the RB method during training, we randomly select a subset of weights in MLP represented by the blue edges and binarize these weights. We fix these binary weights and only update other weights at each step. After several steps, we set these selected weights to their original values before binarization. Then we select a new subset of weights and repeat the above procedure. We can use a mask matrix to implement the RB method easily, and the gradients are also easy to calculate. For more details, please refer to our paper. Now, using MLP and RB method, we can train CIS effectively. Moreover, benefiting from the transparent structure of CIS, we can further simplify the trained CIS by eliminating dead node and redundant rules. We conduct experiments to evaluate the proposed method and answer the following questions. How is the classification performance of CIS compared to other state-of-the-art models? How does the random binarization rate affect CIS? How is the model complexity of CIS? We took 12 datasets from the UCI machine learning repository, all of which are often used to test classification performance and model transparency. To evaluate the classification performance of CIS, we compare the F1 score with other baselines. Decision trees, scalable, Bayesian, rule-list, and logistic regression are transparent models, while SVM, piecewise linear neural network, gradient boosting decision tree, and random forest are complex models. First, we can observe that the RB method is necessary for the CIS training. CIS trained without RB method performs poorly and acts quite differently from its corresponding MLLP. CIS not only has a better performance than other transparent models, but also outperforms all the complex models. Only the random forest with 100 estimators, which is not transparent anymore, has a comparable result. It should be noted that CIS performs not well on the black node and let recognized dataset. The reason is the recursive minimal entropy partitioning algorithm we applied to discretize continuous feature values brings bias to the dataset. To show the impact of varied random binarization rates on CIS with different structures, we train 3 3-layer CIS and 3 5-layer CIS on the UCI Connect 4 dataset using varied random binarization rates for illustration. The result is shown in the figure. The legend labels show the number of nodes in each middle layer. For example, 64 represents 3 middle layers and each layer has 64 nodes. We can see that without RB method, deep CIS performs poorly compared to the shallow CIS, and neither shallow CIS nor deep CIS performs well. However, if we set binarization rate to an appropriate value, for example, in the range from 0.7 to 0.9, the deep CIS can outperform shallow CIS and get a high F1 score. However, For CIS with the same depth, the wide one performs better. Considering that model complexity affects the model transparency, we compare the model complexity of CIS with the decision tree and the random forest. We also compare the model complexity of CIS after different simplification methods. We use the total number of edges in the model to measure the model complexity. The result is shown in the figure, and logarithm is adopted for a better viewing experiment. On most of the dataset, there is no significant difference between CIS and decision tree, while CIS has a better classification performance than decision tree. Random forests need 100 estimators to obtain high classification performance, which leads to extremely high model complexity. To show the inner structure of CIS, we select one rule set from the CIS trained on the ANDOT dataset as an example. The rule set shown in the figure corresponds to one CIS node used for predicting whether the income of someone is below $50,000 one year based on census data. Different types of features are marked in different colors. For example, red for features related to capital. We can clearly see that lacking capital behavior, not being married, short work hours per week, and low educational background may lead to low income. In conclusion, we propose a new hierarchical rule-based model called Concept Rule Set and its continuous version, Multilayer Logical Perception. We can use grand descent to learn the discrete CIS efficiently, while the continuous MLLP and random binarization method we proposed. Our experimental results show that CIS enjoys both high classification performance and low model complexity. And future work, we plan to eliminate the need for data discretization before training and explore the application of our method for unstructured data. That's all for today's talk. Thanks for your listening. Any questions, please email me.